Today we will work with moment generating functions. This is part 2 of a series of videos on moment generating functions. The goal will be to discuss the convergence of MGFs and CDFs and using MGFs to study the distribution of the sum of independent random variables. Let x be a random variable with px, the PMF of x, if x is discrete, and fx, the PDF of x, if x is a continuous random variable. In the setting, the MGF or the moment generating function of x is defined as the expected value of e to the t times x. More formally, this is the sum over all the values of x of e to the tx times px if x is discrete. Else, it is the integral minus infinity to plus infinity of e to the tx times fx dx if x is continuous. Note that the kth moment is exactly the kth derivative of the moment generated function evaluated at t equals 0. Also, if y equals ax plus b is a linear combination, the moment generating function for y is e to the bt times the moment generating function of x evaluated at at. Furthermore, under certain conditions, if two moment generating functions are equal for all values of t inside a neighborhood containing 0, then the corresponding CDFs will be equal for all values of u inside the real line, which means that x and y are going to be identically distributed. We will next state a very important theorem regarding the convergence of moment generating functions. So suppose we have a sequence of random variables xi with corresponding moment generating functions m sub xi t, I going from 1 to infinity. Then we will also suppose that there exists a delta greater than 0 such that the limit as I goes to infinity of mxit converges to mxt for all values of t inside this interval minus delta delta, where mxt is a moment generating function of a random variable x. In this setting, we will have a unique CDF f sub xx whose moments will be determined by the function m sub xt, and for all values of x where f sub xx is continuous, we will have the pointwise limit as I goes to infinity of f sub xi of x to equal f sub x x. This is to say that the convergence of the MGFs to an MGF will imply the convergence of the CDFs to the CDF of the random variable x. Let's do an example to get a sense for what is happening here. So suppose n is a natural number, p is a number between 0 and 1, and lambda equals n times p. In this setting, define a sequence of random variables x sub n that are binomial with parameters n and p, and let y be the Poisson random variable with parameter lambda. We know the moment generating functions for the xn's and the y's given by the following formulae. Note that p in this setting is lambda over n, and then we can compute the limit as n goes to infinity of m sub xn t. You notice that this limit is going to be limit as n goes to infinity of 1 plus n times p times e to the t minus 1 divided by n, the whole raised to the power of n. We'll state a brief fact from calculus. If we have a sequence an that converges to a, then the limit as n goes to infinity of 1 plus an over n, the whole raised to the n, is going to actually equal e to the a. Now, if we take an to be n times p, we know that an converges to lambda. This is by the assumption above. And we can apply this calculus fact to our limit calculation to get that the limit as n goes to infinity of mxn t is equal to e to the lambda times e to the t minus 1. This is exactly the moment generating function of the Poisson random variable with parameter lambda. This says that if n is large and p is small, then the moment generating function mxnt is almost equal to myt. This gives us the Poisson approximation for the binomial distribution when the sample size is large and the probability of the success p is small. This is to say that the Poisson distribution is approximately binomial distribution when we are working with rare events. Note that in this description, both n and p are going to vary and lambda remains constant. We will next talk about moment generating functions where in the context of more than one random variable. That is, we're going to study the moment generating functions for joint distributions. The important theorem over here is as follows. If we are given two independent random variables, x and y, with moment generating functions mxt, myt, these are mgfs of x and y respectively, then if we define the random variable z as the sum of x and y, we will have that the moment generating function for z is going to be the product of the moment generating functions of x and y. The proof of this theorem follows in a straightforward manner. The important fact that we need to use over here is when we are working with independent random variables, the expected value of gx times hy is going to be expected value of gx times the expected value of hy. So that gives us the proof for this theorem. Let's work out some examples where we are working with sums of two independent random variables. Suppose we are in the binomial situation where the random variable x has binomial distribution with parameters n and p. Therefore, mx has the moment generating function given by the following formula. Y has the binomial distribution with parameters m and p. Notice that p is common to both x and y. In this setting, using the theorem, we will have that the moment generating function for mx plus y is going to be exactly p e to the t plus 1 minus p raised to the power of n plus m. This is exactly the moment generating function for the binomial distribution with parameters n plus m and p. By uniqueness of the MGF, we know that x plus y will therefore have to have the distribution binomial with parameters n plus m and p. Next, let us work with the Poisson distribution. So suppose x has the Poisson random variable with parameter lambda. The moment generating function will have the following formula, and y have the Poisson distribution with parameter mu, and the moment generating function for y is going to have the formula e to the mu times e to the t minus 1. Then the moment generating function for mx plus y can be calculated as follows, which is exactly e to the lambda plus mu times e to the t minus 1, which is the moment generating function for the Poisson random variable with parameter lambda plus mu. Therefore, the sum of two independent Poisson random variables is also a Poisson random variable. Next, working with the normal distribution. Suppose x has the normal distribution with parameters mu1 and sigma 1 squared, and y has the normal distribution with parameters mu2 and sigma 2 squared. The corresponding moment generating functions are written out on the screen. And then we can use the theorem, assuming that x and y are independent. The moment generating function for x plus y is going to be the exponential of mu1 plus mu2 times t plus sigma 1 squared plus sigma 2 squared times t squared divided by 2. This is exactly the moment generating function when we are working with the normal distribution with parameters mu1 plus mu2 and variance sigma squared equals sigma 1 squared plus sigma 2 squared. This can be written out as follows. Remember that the important assumption is that x and y are independent. Finally, let's work with the gamma distribution. In this setting, we will have the random variable x to have gamma distribution with parameter alpha 1 comma beta. The shape parameter is alpha 1 and scale parameter is beta. The random variable y is going to have shape parameter alpha 2 and scale parameter beta. Notice that beta is common to both x and y. If x and y are independent, we can use the theorem to calculate the moment generating function for x plus y as the following calculation, which results in 1 over 1 minus beta times t raised to the power alpha 1 plus alpha 2. This is the moment generating function for the gamma random variable with shape parameter alpha 1 plus alpha 2 and scale parameter beta. Therefore, the sum of two independent gamma random variables is with the same scale parameter is also a gamma random variable. It should have been scale parameter. There's the typo in the screen. Finally, let's talk about moment generating functions for a random sample. Yeah, so suppose x1, x2 up through xn is a collection of random variables. We will say that the collection is a set of mutually independent variables if the PDF or the CDF, depending on whether xi's are coming from a discrete or a continuously distributed population, should split into the product of the marginals of the distributions of xi's. And this equality has to be true for all values of x1, x2 up through xn in the joint sample space. F is going to be our joint PDF or PMF, and F sub xi's are going to be our marginals. Recall that if x1, x2 up through xn are mutually independent random variables, we can calculate the expected value of g1x times g2x2 times gnxn to be equal to the product of the expected values of gi xi. Therefore, if we have x1 through xn to be mutually independent, and we define a new random variable z to be equal to x1 plus x2 up through xn, we can calculate the moment generating function for z, that is the sum of the n random variables which are mutually independent, to be the product of the expected value of e to the t times x1 times e to the t times x2 all the way up to e to the t times xn. So our gi xi in this case is the function e to the t times xi. This tells us that the moment generating function for a sum of n mutually independent random variables is going to be the product of the moment generating functions of the random variables that appear in the sum. We can now look at a special case of the situation. If x1, x through xn was in fact a random sample, that is to say that the collection x1 through xn is a mutually independent collection of random variables, and the random variables xi's are all identically distributed to a common distribution, say x, with mgf mxt. In this setting, the sample total, the statistic sample total, is defined as the sum of the n random variables inside our random sample, and we can use the previous result to calculate the mgf of the sample total to be the product of the mxi times t. But since all the xi's are identically distributed, the mgf of the sample total is just going to be the product of all the mxt t's n times, which is mxt to the power n. We can use this fact to calculate the sampling distribution of the sample total. Let's work with the first example, that is the binomial distribution. So if our random sample is coming from a binomial distribution with parameters m and p, then the moment generating function for the sample total is going to be calculated as the following calculation. And notice that if we follow through, we will get that the moment generating function is p times e to the t plus 1 minus p to the power n times n. This is the moment generating function for the binomial distribution with parameters n times m and p. Therefore, the sample total has the binomial distribution. Next, working with the gamma distribution, if our random sample of size n is coming from gamma distribution with shape parameter alpha and scale parameter beta, we can calculate the moment generating function of the sample total as the following calculation shows to be 1 over 1 minus beta raised to the power n times alpha, which is the moment generating function of the gamma random variable with parameters n times alpha, that is our shape parameter, and scale parameter beta. Finally, suppose we have n mutually independent random variables x1, x through up through xn, and we use these to define yi's, which are going to be a linear combination of ai times xi plus bi, where ai's are real number, ai bi's are real numbers. In this setting, the moment generating function for the sum of random variables y1, y2 up through yn is going to be e to the t times the sum of the bi's times the product of the moment generating functions of the xi's evaluated at t. Notice that if we take ai's to be 1 over n and have all the xi's to be identically distributed, we could use this theorem to calculate the distribution of the sample mean x bar. To summarize this video, we have introduced the idea of how we can use a sequence of random variables to determine the CDF of a limiting random variable. We use this to show that the Poisson random variable approximates a binomial random variables when we are working with large samples and rare events. We then spoke about how moment generating functions could be used to calculate the distribution of the sum of independent random variables. We generalized this idea to the case of calculating the moment generating function of the sample total of a random sample, and we did a bunch of examples. We will come back to this idea when we are working with the central limit theorem. But this is all for now. Take care of yourselves, and I will see you around.